So in the last few videos, we have been talking about matrices, how and when they are equal. We also talked a bit about the special types of matrices. Let's talk about addition. Let's talk about addition. So since matrices are just a collection of numbers and you can add numbers, you can also add collection of numbers. So you can add two matrices. So let's begin with a perhaps a practical example. So let's say that Sam, or let me not take names. Let me just take a person A has some notebooks, some pencils. Uh, so let's say notebooks and pencils, and let's say he has 5 notebooks and 2 pencils, and similarly for B we can write the matrix as being 3 and 3. And what you can do is, let's say A and B decided to give all of their possessions to a third person named C who had nothing with him. So C would basically get 5 plus 3 notebooks. 5 plus 3 notebooks that arise from the fact that there are 5 and 3, so 5 plus 3 notebooks, and 2 plus 3 pencils. And so what we're just doing is we are adding both the matrices element wise, and you can not only just have a row matrices, you can extend this to whatever application you want. So if you had let's say for example two matrices, A to be equal to root 3 1 0 1 and B to be equal to root 5 2 1 0. If you add both of them, what you're basically doing is you're taking all of the elements in this all of the same elements lying in the same position in the matrix, and you're adding them element wise. So for the first part it would be root 3 plus root 5, so root 3 plus root 5. For the second entry in the first row it would be 1 and 2, so 1 plus 2 will be 3. Then you have 0 and 1, so 1, and 1 plus 0, so again 1. So as simple as that. You take the individual entries, you add them, and that would just result in the sum of two matrices. You could let's say you, instead of having this matrix, having this 2 by 2 matrix, let's say you had a 3 by 2 matrix. Let's say A was 2 by 2 and B was 3 by 2. So let's extend this matrix with sort of random numbers. So let's write 2 more numbers here. So let's say 1 and 1. Now if you want to add these two matrices, if you want to figure out what A plus B is in this case, you can do the operation, you can do the addition operation for these four entries, but then for these two there is no corresponding element in A. So you can't really add these two matrices. A plus B is just not defined. So for addition, the orders of the two matrices should be the same. Orders should be the same. And that makes sense. You can't add two collections which have different numbers of rows and columns. It won't just make any sense for saying something like that. What you could also do is you could subtract these matrices. And what I mean by subtracting is, let's say we just continue with the example that we had. So let's erase the additional numbers that we had just put in. And again, what subtraction is basically is you're taking the element wise difference. So these are the two matrices. So A minus B is equal to, well, you take root 3 and you subtract root 5 out of it, so root 3 minus 5. Second, you have root 1 minus 2, so 1 minus 2 is negative 1. Then you have 0 minus 1, so that's again negative 1. And then you have 1 minus 0, and that's 1. As simple as that. So if you want to write it, in a more sort of a mathematical way, you would write that A equals Aij and B equals Bij. Then their sum A plus B would just be equal to the sum of the elements, the collection of the sum of the elements. And if you want to write the difference, then you just do the element-wise difference of the elements. And after defining what the sums and the difference of these two matrices are, what we can do is we can specify some properties. So we have a few properties of adding real numbers. We have commutativity, we have associativity, we have the existence of an additive identity. So that means that if you take any number 3, or let's say root 3, and you add 0 to it, it just results in the same number. This number is sort of the additive identity. And you also have the existence of additive inverse in real numbers, and sort of the same properties apply to matrices as well. So let's start with commutative law of matrix addition. We are talking about matrix addition, and in matrix addition, firstly you have commutativity. So it doesn't matter whether you add A plus B or B plus A, it's just one and the same thing. So if you want to prove this statement, so A plus B is just Aij plus Bij, the collection of these elements, and B plus A is Bij plus Aij. Now we have already established that commutativity exists for the real numbers, for complex numbers as well. So since all these elements would be equal, and since all the elements are equal, the order is equal, then these two matrices would be equal as well. And yes, the general scheme applies that if you're adding any two matrices, or any 3, any 4, any number of matrices, all of them should have their orders to be same. The same number of rows and the same number of columns. Let's say you want to talk about the associativity or the associative law of matrix addition, and what it says is it doesn't matter in which order you perform the operation. So either what you can do is you can add, if you have 3 matrices, again same order, and 3 matrices ABC. So if you first add ABC and then add the resultant, then you add the resultant to C, or you do something different. Let's say you do B plus C first and then you add it to A. The resulting matrices would just be the same. And in this case also you can prove it by taking the elements to be Aij, Bij, and Cij of the 3 matrices. And since the associativity of real numbers and complex numbers already exists, that's something that we have already established, the associativity of matrices containing those numbers would also exist. We also have the existence of additive identity. Additive identity. So what that means is the additive identity in the case of real numbers or complex numbers is, let's say you have a complex number 1 plus I, then you can add the complex number 0 plus 0i and you could still get the same number. It's just common sense. So if you take a matrix, of any order, let's say you take a matrix of having 2 rows and 3 columns, and you fill it with random numbers. So root 2 pi I 1 0 1, and you add the zero matrix. The zero matrix, as I talked about in the previous videos, is just having all its elements to be 0. If you add that, then you just see root 2 plus 0 gives you root 2. Pi plus 0 gives you pi. And since all the entries in the second matrix are 0, you just get the same matrix back again. So it means that for any matrix of the order, for any matrix A of the order m by n, you add a 0 matrix. Let's represent the 0 matrix by a big O. You have a 0 matrix of the order m by n such that adding them doesn't change anything. You still get the same matrix back. Great. So we have so far established commutativity, associativity, and the existence of additive identity. The last one is the existence of additive inverse. Additive inverse. And what that means is once you have established the additive identity, you have something that's called an additive inverse. And so if you take the real numbers for an example, so you have 2 and you want to get back to the additive identity, which is 0 in the case of the real numbers. So you always have a number, in this case -2, such that adding them gives you 0. If you have a number I, the complex number I, you can add the number -I and you would get 0. You can extend that. You can extend that to matrices. So if you take the same example that we had before, so root 2 pi I 101, you want to make this matrix of the order 2 by 3, so A 2 by 3, and you want to make it into a 0 matrix. That's the additive identity for 2 by 3 matrices. So what matrix would you get to ensure that you get by adding to it the 0 matrix? So what you do is you just write the negative of all the elements. So for root 2 you write negative root 2. So root 2 plus negative root 2 would give you 0. For pi you write negative pi. For I you write negative I. Then -1 for 1, 0 just remains 0, 0 plus 0 is just 0, and then for 1 you again write -1. And notice this is just same as saying you write negative a, and that's a concept, that's the concept of scalar multiplication. That is, you multiply this matrix A by a certain number. In this case, -1 multiplies by A, and you get a resulting matrix. And this is an idea that we'll explore in the next video. For now, you can also regard the existence of an additive inverse as the existence of a matrix, so that you can subtract the original matrix and get the 0 matrix of the same order. So the properties of matrix addition are a lot more common sense because they're derived from our common senses of the addition of real numbers. And so matrix addition and subtraction is fairly easy. And I'll see you in the next video where we will talk about scalar multiplication. See you in the next one.